Hi everyone. Yeah, thanks a lot and sorry for the slight delay. So this is going to be a PDF. Normally we'll have some videos also included, but you will have to imagine things. So first of all, I'd like to thank the organizers for the honor of being here. Like I was studying, I guess, like 20 years or so, a couple of buildings below. So it's the first time I give a presentation like that at my first university, so that's nice. I'm going to discuss today our my work and my team's work on what I call cyberphysical AI towards an AI, robot AI scientist. I don't know if you have already heard the term AI scientist. I thought it's not complex enough, so why not also add a robot in the loop? So I am an associate professor at the University of Amsterdam, working on dynamical deep learning. And specifically, I'm interested on its applications in robot learning, causal interpretations and mechanisms, as well as AI and science. And let's start with some motivation. Why would we want to have physics better integrated into our robot learning, into our machine learning, and our computer vision systems and algorithms? There is, the past couple of years, the concept of semantic truthfulness. So for instance, when we use ChatGPT or whatever LLM, you can pick your poison, a fundamental question is to what extent these LLMs, that they generate answers, they don't just copy-paste answers based on some sort of retrieval mechanism, but they're generating these answers, to what extent these generations are truthful. So for instance, the fact that Paris is a capital of France, it's a true statement, right? Like it doesn't, you're not going to debate that. And of course, when you're generating something, there is no guarantee that you will have such truthful statements, or at least until so far. So semantic truthfulness is a very important one in terms of trustworthiness, making sure the algorithm turn up doing silly things and whatever. We want to, our algorithm to know that water freezes at 0 degrees or that the Earth orbits the Sun, because if the algorithm cannot do that, then it means that, how else can you trust for even more important things? Now, there is semantic truthfulness, and this has taken the biggest, let's say, stake. However, I argue here that there is also physical truthfulness that algorithms have to abide by, especially algorithms that equip our robots or our Internet of Things cameras, whatever, things that have something to do with the physical reality. Now here there will be a video of the robot moving things and how an object cannot intersect the table. And if it does, then that's not just a mistake, as we would normally have in our computer vision benchmarking, but it's a physical implausibility that would create actual real problems to the robot. You have to imagine the video. Now, physical truthfulness is very important when it comes to trustworthiness and safety. And here there will be normally another video of the Google VO or OpenAI Sora. I guess you know these latest generation engines, which generate arguably fantastic videos, really plausible. Although when you actually start digging in, it's not that obvious that they work that well. And yeah, we want this physical truthfulness now. If we want to, for instance, generate I don't know, scenarios for our traffic, traffic planners, or for our robots, in the bottom left tile, there was a Unitary robot in China that started behaving erratically all of a sudden. Yeah, we don't want that. We want our robot to know what it's the physical space around it and make sure that doesn't, it doesn't become dangerous. Now, there are a lot of applications that need trust, and I think that actually we're not there yet. The algorithms are currently being more and more deployed, but we will see this a lot more in the coming years. And then you do need trustworthy algorithms, like algorithms that can understand the physics better and better, such as in robotics, in self-driving, of course, in the Internet of Things, in AI communications, logistics, AI for industry. Basically, wherever AI will be deployed on site, this has to be done correctly. The way, like, so what I say to the colleagues when I have such a conversation is, I would not trust a robot next to my kid if it has been trained only on ImageNet and it can confuse a cockroach with, like, you know, like his hand, whatever. Like, I mean, you have to have like some sort of like more guarantees. Now, what do I propose here? Like, so that's like, let's say, the motivation, the context. What do I propose here is perhaps we can use science as an invariance. And what do I mean by that? What we know until now is our machine learning system. So like the crux of machine learning, one way or the other, is some sort of invariance. So you can think of like supervised learning as an invariance learning mechanism where you basically want to map data to some like invariant labels, like labels that they don't like change over time. Yeah, of course, you wanna like learn this as accurately as possible, but the definition is that. And now we have other types of machine learning, let's say frameworks like self-supervised or unsupervised or reinforcement learning. All these have one way or the other a notion of invariance. So for instance, in unsupervised learning, the invariance is that you have to make sure your input and your reconstruction of the input is invariant, doesn't change. Or in self-supervised, you literally take two different like small deviations of the input and you want to make sure like they map to an invariant representation, that they are like as identical as possible. Now, science is actually invariant in the sense that, for instance, Newtonian mechanics or like gravity and whatever, like that, you know for sure applies to every location on Earth, like, okay, like roughly speaking. And yeah, one could also say that this is also how we ourselves learned how to navigate this world. So what if we use this type of like invariance in scientific like principles and laws to use it as an overall learning objective of our robot AI? And I think that perhaps it's quite interesting in the sense that it's a bit less anthropomorphic and thus a bit less biased. So I was thinking how to organize this, like also in relation to my own works, and this is what I came up with. So I think like if we were to use indeed science as some sort of invariance, we would have to first like somehow convert the world pixels, so what like our observations or measurements or like your RGB values and whatnot, like from these uninterpretable values into some sort of symbolic form. They have to be symbols. So when you have an object detection or a segmentation, that's a symbol, right? Like this cup is, of course, you can think of it as a bunch of pixels, but I think in reality what really happens is that you say, well, this is a cup, right? Like you attribute to it all sorts of symbolic attributes that relate to its function. Now, once you've got that, you can do some sort of like mechanistic representations. You can say, like that's a cup. You can like lift it. It's not too heavy. It's a bit hollow, right? Like, so you can put something relatively heavy. You can put water, or you can put like some other liquid. You should not put something that's too hot or too heavy, because then it'll tear up. So there are all sorts of mechanisms that relate to like the notion of cup. After we got like experimentation with the world, so once you actually have this basic understanding of mechanisms that apply to the particular symbol, we can actually do experiments. I can like start pouring different types of liquids in the cup and see how it behaves when it breaks, or what can you do with it. And in the end, you would like to have some sort of like validation, cyberphysical validation. So basically, you want to connect how my AI, my purely digital model, which for me is like really shocking, like it's completely deprived of any physicality, of any physical understanding. Like it's completely, whether you run it on the cloud right now, the machine learning models, or in a robot, it doesn't make a difference. Like you literally use the same algorithms, right? Like you literally use the same code, or nearly the same code. There is no difference. How you're going to connect its outputs to the physical reality of the world, I think that's something very interesting to decipher. So, can today's generation model understand physics? I start from the last part and I will back propagate. So, cyberphysical validation. In this work, ongoing work, what we did is quite simple. We took the latest video generation models, like Veo, well, we wouldn't take, I'm not sure if we take Veo, but OpenSora, like Cosmos from NVIDIA and so forth, and we benchmarked them with respect to their physical reasoning capabilities. And we did that with actual physical experiments. We did experiments in the physics lab of the University of Amsterdam, like this pendula, or like shooting objects in the air, and we recorded them, and we saw how well they can, like how well can these models generate physics and understand physics thereof. So the overall pipeline, before I go into the details, is as follows. You got the video generation above, which is, well, we just use the not the convention, like the standard generative models right now, like Cog Video, Cosmos, Pyramid Flow, LTX Video. We prompted them with text, and additionally we could also condition their generation on a couple of frames. So first we're recording our experiments in the lab. We're taking the first couple of frames, for instance, of the pendulum that was about to move, and then we would ask our generative model to generate the rest of the trajectory. And after that, what we did was the following. From the real world video, so the ground truth video, let's say, as well as the generated video, so the ones that were generated by any of these models, we were doing some combination of segmentation and tracking to get some with depth analysis, automated depth analysis. For all this, our basic idea is that today's foundation models are so accurate and so strong that are good enough for doing more advanced processing. And I'll go a bit more into the details. Whether they are actually that accurate and that good, of course, is something that also has to be tested. Anyways, from combination of these tools, we were able to extract trajectories and then obtain these like dots, these bullets, which are basically measurements. You can create plots out of them. Now, maybe one thing that I'd like to say here is that, anyways, from the video, what is hard when you actually start using, so why can't we do physics already? Why is it so hard to incorporate physics or validate physics from videos? Well, the main difference is that physics is actually a study that makes a very strong assumption. And the assumption is that it operates on perfect state variables. It assumes that the world is completely known. So in other words, it assumes full observability, or one way or the other, even the unobservable part is very well contained in one way or the other. You know perfectly what is your velocity, or you assume that there is a single perfect velocity. You assume that you've got a point mass. You make all sorts of assumptions, and of course, when these assumptions don't hold, the actual equations don't apply, or they don't apply that accurately. And then you have to make things a bit more complicated. But even when you make things more complicated, you have to somehow integrate out the uncertainties. You have to make sure that everything is under your control. However, for AI, this is anything but, right? Like when you're generating something, you have no control. You can only assume partial observability at best. Now, why I'm saying all this? Because when you're actually trying to assess the physical understanding of a generation of a video, especially of something that in principle never really existed before, how are you going to apply the physical law that assumes point masses, right? Like you don't even have ground truth. It's not like you can cheat in quotes or whatever. So in other words, we want to somehow obtain perfect state variables. And for that, we do the simple thing. We use segment anything too, which basically does segmentation and tracking using prompts. And then based on that, we can extract consistent object trajectories over time that you can then convert into some sort of like, like history. We compute the center of mass of objects, we estimate velocities, accelerations, and so on with central differences. So nothing really, like pretty basic stuff. And on top of that, once we have these perfect size variables, we're using the so-called physics-informed neural network architectures. Have you heard of physics-informed neural networks before? Can you raise hands who has heard before physics-informed? Right, not too many. Now, physics-informed neural networks is actually, I wouldn't say it's a Greek invention, but it has been heavily popularized in 2000, what was it? I think 17 or 18, by George Kamiarakis' group and Paris Pervikaris in UPenn, where basically they say, this is like what they say, like they come from mechanical engineering, and they say, like when you got an ODE, which is like y dot equals f of y, that describes a physical law, for instance, equation of motion or whatever, what you can do is you can train a neural network to minimize, like to use this like ODE as a loss function, and then you train a neural network to minimize this particular loss function, your loss ODE. And you can do that basically, when you do that, we don't even need data. So basically in that case, you're using the neural network as an optimizer. And on top of that, you can pair it with data observations that you might have. Now, why would you do that? Well, when you have something very simple, like a very well-known like physical setting, you don't really gain much. However, this approach can have tremendous impact when you have quite some data and not good enough knowledge of your physics. And by not good enough knowledge of your physics, I'm not saying like you get a student that scored 12 out of 20 in the exams, but more like that your physical setting is more complicated than the known equations. So in that case, you can actually use a neural network to basically fit your observations and then be able to predict what's going to happen next. Now, with these physics-informed neural networks, we can learn to solve physical problems if we know our variables y, and if we know the general form of our ODE. And in this case, exactly because we have already obtained the perfect state variables, which is our y, and because we know the ODEs, because we can prompt the video generative model, like for instance to generate a pendulum moving or a double pendulum or what have you, then we can combine these two and assess in a very quantitative and a very rigorous manner how well the generative models can understand physics beyond just physical assessment, visual or human assessment that previous work have done so far. Normally, here we would have also another video that would show how physics-informed neural network works, which basically, where basically the blue line is, for instance, the output of the neural network. The orange dots are the observations. The damped sinusoid is the physical setting, the ODE, and then the neural network learns to fit basically the ground truth. However, not greatly, so it fits very well applications where the data is, and beyond that, it doesn't. Now, based on that, what we did is the following thing. We first of all, because we know the ODE and we have the state variables, we define the equations of motion, we can write them down very clearly, and then use physics-informed neural networks to fit precisely a neural network that should satisfy that equation, the said equation. So in the top right corner, you see a real learned trajectory. So from a real video. So we obtain the state variables there, which are the dots, the perfect state variables, which are the dots. And below, you do the same thing, like a repeated process, but now instead of using a real video, we would use a video generated by a generative model. And as you can see, it looks quite similar, but not exactly, right? Like for instance, in the real learned trajectory, I think that's for, what was it? Yeah, probably a pendulum, something like that, like there's some sort of damped oscillation. You see that the period of the pendulum decreases over time, right? Like in the real video, whereas in the generated learned trajectory, you see like this pendulum motion, this oscillatory motion, but it's not damping, right? Like it starts a bit weird with some noise, then it increases, then it then it increases, then it decreases again, and so forth. So you always start seeing that actually the models have learned quite something about physics, the generative models, but not good enough to be able to trust them, right? Like, if, for instance, if you had a car that had to swerve such, like, I don't know, obstacles, probably would have trouble figuring out the precise physics to take the correct actions. Now, right, so for the dynamical score, what we did is we basically computed the normalized mean squared error of what, what the general trajectory is from what is the real one. Can you think of one case where this would fail? This is not a perfect score. That's the best that we could come up with until now. But what is the problem when you're trying to fit an actual equation, such like that, like more general equation, to a generated like video? Like, for instance, if I have the, f equal m times g, like for the following object, what's the assumption there? Yes?
No error.
Sorry?
It's in the void, no error.
No error, yes, good. Correct, very correct. That's also, but like something even more like explicit, yes?
I would imagine that specialization effect, for example, situations, the way it's guided affects the staging distributions or deviations, so that is those effects.
Yes, but I'm asking for something even more basic. Yes?
When there is a delay.
Delay. No. Something more. So basically, you assume that the gravity, like the concept of gravity, is like 9.81, whatever, right? How would the generative model know that? Like, actually, how can the generative model know that the ball is falling on Earth and not on Mars? Whereby, for instance, you would have a different, like, you would have the same type of equation, but a different gravitational constant. Maybe the model, the generative model, knows how to generate, it just doesn't know how to generate something specifically on Earth. I don't know, like, you don't know, especially because you feed it with like thousands and thousands and thousands of data, or millions of data. It's very hard to assess this. And okay, with gravity, perhaps you could say that arguably that's not too complicated, but when you try to make this more general, like, for instance, assume that you don't see the ball falling like that, like from gravity, but assume now, and that's, I think, the most interesting case, like this is just the first step, assume that you're looking at it from an angle, whereby your equation of motion is not even like correct anymore. You have to do some sort of like orthogonal projections, or you have to like to adapt it to the particular situation. The thing is that in that case, the equation is not exactly correct. So you can try to like some sort of like to match it, but it's not like straightforward how you can, like whether the difference is because of different constant factors or because there is something fundamentally different in the equation. Yes? Yeah, sure. Of course. You can do all sorts of things, but like now we're talking about the most abstract, the most general setting. Now, once you got like anyways the physics-informed fitting on your data, you can also compute physical invariance score. So for instance, there is a preservation of momentum or horizontal momentum in the case of like a moving object, like a pushing object. And based on that, you can also make sure that, or you can evaluate not only how well the trajectory fits, but also how well these conservation laws are satisfied in the video generative models, which is perhaps even more important in terms of like physics. So based on these two scores, we had also a third score, which is the discard rate, and perhaps that was also the most, from practical perspective, most important one. Basically because the generative models were producing a lot of stupid things, like both disappearing or having like duplicate pendula at the same time, or basically stillness, which is also, however, a very interesting case, because how do you know like that the object is supposed to move, like unless you really engineer it? I mean, so explains, it describes an experiment. And anyways, we were creating this, we were filtering out these, let's say, corner cases. And with these two metrics, plus the discount rate, we created a leaderboard, a benchmark, whereby we saw that based on the actual physical laws, most of today's generative models are not that great. They're not terrible. They're simply average. And of course, we can do much better. And when we're doing the experiments, we didn't include V3 from Google DeepMind. That hadn't been released yet. We tried afterward, and it was doing better, but certainly not perfect. So overall, we see, we tried 6 physical experiments, like falling ball, bouncing balls, projectiles, harmonic pendulum, non-harmonic pendulum, and double pendulum. And you can see that, in most, so falling ball was one of the easiest. Bouncing ball was hard because it has to really learn the physics of bouncing. Double pendulum was also surprisingly quite okay. Of course, the next interesting thing will be how you can now use this type of metrics to bootstrap your video generation to make it more physical. And I think that's one of the most fascinating questions at the moment. Whoever cracks this problem open will certainly attract the interest of the likes of NVIDIA and Google. How much time do I have? 25 minutes.
It's 25 plus 3 minutes, 28.
Because I have a watch now. Is there a watch on? Anyways, so from cyber-physical validation, going one step before, on experimenting with the world, so can we have our robot scientists form a hypothesis, well, not form a hypothesis, but do experiments, given hypothesis, do an actual experiment with the world. So in the next work that we just published a couple of months ago, one could say that we're trying to think whether robot learning can benefit from explicit physical modeling that would be required to perform physical experiments with the world. So this work is called, it's about compositional, it's what we propose is compositional manipulation world models, and relate a bit to the previous talk with physical simulators and with tagline dream to manipulate. So this is about basically how we equip robots and anyways our machine learning algorithms with an element of imagination. So if I will have the picture of the White Tower of Lefkowsky here, if I cover most of it, you can still imagine what the rest of the scene is like, because you have this internal mental model in your mind. So basically, imagination helps us recreate past experience and thinking about new possible scenarios, as well as it also helps us plan how to perform a task. So for instance, in the bottom picture here, we see a boy, or a man, I don't know, solve Rubik's Cube blindfolded. Now, to me, that's amazing. I mean, I don't know, I cannot even solve it with open eyes. So this guy can do it. But how can you do it? He cannot even see the colors. Well, there is, of course, an algorithm, right? That if you follow, you're always going to solve it. But that's not the point. The point is that he has an internal mental model of how the Rubik's Cube is at any moment, and it can use it to actually solve it, to do a highly sophisticated task. He can use it to predict the consequence of its action, of his actions, and how to even solve new tasks, perhaps. And why would we need imagination? We need it, what we propose here is to add this kind of imagination, if possible, or to combine, to integrate this imagination with world models. Now, world models, in my opinion, again, in my subjective opinion, will be one of the biggest trends in the coming years. And what is a world model? So you can think of a world model as an external, in quotes, as an out of robot or out of body, out of robot body type of model, which given current world state, ST, and a possible action state that I'm supposed to like do at this very moment, this model can predict the next world state. So in that sense, it converts world dynamics to space type model. Like for instance, if my world model is about this auditorium, and then like I can know pretty much everything that happens, and not happens, but like, yeah, the state of everything here. If I do an action like I take this and I throw it, I can predict what's going to happen, right? Like it was going to fall somewhere, it's going to break down. If I hit somebody, he will get angry or she will get angry. So I can create this type of future prediction given what I can see now about the world and a potential, a hypothetical action that I will be making. Now, ideally, we would like to use neural networks as world models. And as a matter of fact, there have been quite some influential works that they've done that. The most, I think, like famous of is called Dreamer from Google DeepMind from 2018 or 19. However, I think these models have some big enough problems such that they are not easily deployable in practice. And what are these problems? Well, to put it simply, I think world dynamics are largely local. They're not, of course, all local, but you know, like if I take like this again, this, and I throw it, this is a very local action, right? Like the rest of the world is not going to be influenced by my action. The state of this pointer will, of course, be influenced, and perhaps the state of the area where it's going to land is going to be influenced, but like other rooms or other people far away or other chairs far away will not be influenced. So like the world dynamics are very local to my type of action. In the case of the Rubik Cube, when the boy twists the side of the Rubik Cube, it holds, only that Rubik Cube changes, not all the rest of the Rubik Cube changes. However, neural networks are really not like that. They're infamously hard to model local changes. I don't know if have you heard of disentanglement in neural networks? Can you raise a hand if you heard the term disentanglement? No. So basically, a neural network is like this schematic in the bottom right corner, where you basically feed your data, for instance, an image cut, and then it produces like features, like on the right-hand side. Now, the disentangled representation would be a representation where each of the node, each of the neurons would correspond to one and only one concept. So, for instance, color, or the type of stripes, or the type of shape that the input like pertains. Now, I guess you've seen neural networks before. Do you see this like this type of behavior? No, right? Like everything is completely mixed. The neural network might be fantastically accurate, but you cannot really interpret its individual features, its of individual neurons. So it has very much entangled representations. Now, if you have like that, like for instance in my world model, like with a kid with a Rubik's Cube, this would mean that if I would change specifically like some pixels on the Rubik's Cube because of my action as a robot, let's say, basically all my representation would change entirely, right? So the world model can predict in a way, could predict actually what's going to happen, but I cannot control it in a way, right? I cannot just change one small thing and have a controllable change in my output. Now that's a huge problem because, well, world dynamics are largely local. So if I have a robot which has to decide among all types of like actions that it can take, and it wants to reason what kind of consequences this action have, how it's going to do it. Like basically it has to like try all sorts of different actions in the input. It will get a bunch of different representations in the output. In an exponentially hard vector space, and then it gets harder and harder, especially because world models and worlds are supposed to be open. If you have an closed world with only very specific types of possible changes, that's not a problem. But if you have open worlds, that's actually soon becomes intractable. Now, what they thought to propose then instead is, can we create a physical world model from images of an environment to make the robot capable of imagining, making the, like having a more like, local world model, more like a disentangled one. How can we do that given that neural networks are not helping us, they're not making our lives easy? Now I'm going to introduce a third new concept here, which is Gaussian splatting. Do you know Gaussian splatting? Has like raise, 1, 2, 3, 4. Right. So Gaussian splatting is basically one of the, well, that's also a Greek invention actually from Tertakis in India, in France. Well, I think he was using older concepts from non-Greek, so. But anyways, it's impressive. It's like the state of the art in graphics reconstruction. So basically it's a rasterization technique that allows real-time rendering of photorealistic scenes learned from small samples of images. So basically, like if we put it simply, if I were to take my phone, I forgot my phone, but like, okay, let's say I had it, and then like I would like go all over, like the room. Then I would take like the frames. I could actually use all of them together to create a very realistic 3D, like 3D model of the whole environment, of the whole scene. Very fast in rendering, very fast in the optimization, high quality rendering, like extremely high quality rendering. Again, it's a PDF, so the link is lost. But if you just check Gaussian splatting, you'll see impressive results. Quite good depth estimation and an explicit representation. Intuitively, what Gaussian splats are, you can think of them as you're taking a collection of all these 2D frames and you're computing some sort of like 3D pixels in space. That's it. So you can think of like Gaussian splats as some sort of sparse 3D picture of the world, which you can estimate, you can compute from a set of 2D images of the world. Now, this was originally proposed for graphics, for how to make pretty, let's say, reconstructions of, I don't know, monuments, landmarks, objects, and so forth. We propose to like go past that and combine it with a fourth concept, which is not new, but maybe new for this particular purpose, which is physics engines. So actually, in connection to the great previous talk, we thought, now we've got actually potentially an algorithm that can recreate the 3D world very accurately, so the very, very accurate 3D world states. And physics, why would we even learn it? Like, why would we follow the approach of Dreamer or many other world models and try to reverse engineer the physical laws? Like, the physical laws are supposed to be invariant. Why would we try to fit a neural network here? I mean, there are good reasons, and I'm not saying that we'll not try in the next paper, but at least to me it sounds a very reasonable question that I asked like to myself, that like you have to be able to give an answer. Now, the good thing about when you're using physics engine is that you can for sure be truthful. You know the physics like beforehand. Of course, you know the limitations of the physics, but you know where it's supposed to work. And for as long as you can say something about how accurate your representations that go into that physics is, then you can be pretty much guaranteed on what's the expected outcome. So if you have perfect state variables such as precise object-safe locations, the physics engines can model perfectly all the physical world dynamics. And this was also a video of this three-body problem, three connected body problem, as it bounces and like it was moving in a way very similar to like, to the previous demo. So what we do here is the following. In our robot, so this was also with a real robot done, it works in real life. We first adapt Gaussian splatting. We propose to change Gaussian splatting so that instead of the whole world, we're reconstructing only specific objects, like in an object-centric way. We do it for the bucket, we do it for the various boxes, we do it also for the robot. And then once we've got this state information, we pair it with a physics simulation, specifically PyBullet. And this means that we can apply the physical law and we obtain the update of our Gaussians. So our Gaussians and the Gaussian spots, which are basically 3D coordinates in the world, just move along according to the physical like updates, and then we can basically see a novel Gaussian splatting scene, or like worldview, under set transformations. Now, how we can use that? Well, again, that was a video. Well, you would see like that this is a 3D world that you start moving the objects and basically imagine how the world would change under particular actions. So how we use it is, you can use it like, the simplest thing you can do is imitation learning. So imitation learning in robotics is basically so you normally have reinforcement learning. So reinforcement learning is like algorithms that learn policy functions, so basically functions that can control actions of a robot, let's say, or of an agent. And imitation learning is one way of learning such a policy function, whereby instead of trying to maximize a reward, the Q function or whatever, you collect data, expert data from observations, from demonstrations, like from other robots or from humans performing these tasks, and you simply try to imitate them in a supervised learning type of approach. So instead of doing reinforcement learning, you're using imitation learning. Now what we do here is with Dremel, with our framework, because now we have a perfect, well, perfect in quotes of course, like world model that we can apply physics on. We can perform all sorts of physical experiments in our imagination space, in our imaginative space, see like the consequences, because like the physics engine can tell you this precisely, and we can, and exactly because Gaussian splatting is so photorealistic, we can use it like to generate novel synthetic views, novel synthetic examples that we can use to train our robot better. And it works with a real robot in a few shot settings. So only with 4 examples, we show the robot like 4 cases of what it should, like the task it should learn, like pick in place, pick block. We had like 10 or 20, 15 tasks in total. We showed only 1 or 2 or 3 examples. We augmented it like 100-fold, or not 100-fold, but 100 more examples. And we saw a really great increase in generalization and accuracy. First in accuracy, so in distribution you see quite nice improvements from 55 to 90, 30 to 35, 40 to 80. But what was even more impressive, it was the out of distribution, because exactly we could do all sorts of like adversarial experiments. We could like do all sorts of physical experiments that the model could never have seen because it only had 4 examples in its disposal. We could now really like help with generalization tremendously. It's a pity because the video would show like how the robot does this, like, and it works pretty well. Like, to be very transparent, I'm not a roboticist myself. Like, I did computer vision, and when I was doing few shot classification, I was doing it with stupid little birds, and I was like only 10 years ago. So in 10 years, we managed to have few shot learning work from small little pictures to robots and robot tasks, which I think is impressive. And now that we have something like that, although again in a very like let's say confined space. Anyways, what I think is very interesting is, could we have the robot rediscover world physics and like physical dynamics? So now that we have perhaps all the framework for experimenting with the world, could the robot do experiments? Like, for instance, reverse engineer or infer like the friction of a table, or the like weight of an object, or of like any other physical parameter of the world. 10 minutes. Okay, we're almost done. After experimenting with the world, very quickly I will go to the last 2 parts, which are a bit more technical, more mathematical. One is on mechanistic representations. Can we inverse learn the scientific mechanisms of data? And for this, like this corresponds to like a body of work from the last year that we had in ICML, ICLEAR and ICML again. Like, well, actually it's being presented as we speak, on so-called mechanistic neural networks in collaboration with Francesco Locatello and Adil Purvis in the institute, ISTA Institute in Austria. so basically, our idea here, our concept is like, so basically our question is, if I have data, could I use neural networks now to discover laws, like scientific laws, physical laws from the data autonomously without any like guidance, or with as little guidance as possible? Now, what does this mean? The biggest problem, the biggest question here is, how can you represent like this dynamical or physical knowledge? Well, the way to do that is basically with an equation, right? Like when I tell you F equals M times A, or kinetic energy, like dynamic, like potential energy, and so forth, you always understand this concept in terms of equations. So what we try to do here is exactly that. Like, let's say we have data, we've got observations from our world. Can we, instead of predictions, derive equations? And one equation that like describes basically the observations. In a way, this is trivial. Anyone can produce an equation. Like a neural network, as a matter of fact, is an equation itself. The whole point is whether we can guide the equation to be interpretable, to have like some sort of like physical meaning, and so on and so forth. And how can we do that? Right. So what we want to do here, our basic idea is as follows. Our neural network is basically, you can think of it as some sort of like, well, it's already an autoencoder, but it has a mechanistic encoder here. And UT is the output, is like, let's say, the result of the symbolic equation that you would have if you had the symbolic equation in the first place. And what we propose here is to have in the intermediate representation a generalized family of equations that we could describe any types of like dynamics that you might have. And of course, generalized means that you as a modeler, you have to add what kind of inductive biases, what kind of model design choices you want. Then the task of learning here is finding out which of the terms you'd like to have, like would you like to optimize to find the correct terms in your physical equation. And once you have that, like the basic idea of what we do is we've got a ODE representation here. So by selecting some of these coefficients, we obtain an ODE, like a very succinct, a very compact ODE, which we have to then solve. We have to like solve it in time and then see how well our solved ODE matches the observation. So rather than actually going directly into prediction, in predicting like physical observations, we first have the model propose an ODE, like propose it, like let's say the generative mechanism, the causal mechanism, the physical mechanism, and then solve this causal mechanism to see how well it fits the observations. Now you can use that like to predict and forecast. Like for instance, well, this is an ODE, I don't know the name. I think it was, no, I don't remember. But you can also use it to discover. So let's say for like physics discovery from data. Now, to have a model like that brings a lot of problems. First of all, we want to have any type of sparse and dense data, be it images or like state variables, like from trajectories. We want to be able to, so our ODE representation here has to be very flexible, as flexible as possible. It has to cover like the most general ODE versions out there, because then the model has the flexibility to find the right one. In a way, we like the fact that the neural network is a universal approximator. We don't want to hurt its ability to find the right ODE. We want to have a native end-to-end like neural solver here for the neural. Like if we want to solve an ODE, like the problem is that like an ODE is basically an autoregressive function. It has to solve, you have to like to generate one number at a time. And that's not a great thing like with neural networks. Neural networks, like parallelization, like parallel computation, when you have to generate something one at a time, like for instance with LLMs, things become slower. And that's like why like research teams try to find tricks to make this as parallel as possible, especially with batch parallelization. Some other challenge that we have is that we basically have no ground truth for our ODEs and our PDEs. We literally cannot assume that, like that's our, let's say, like baseline assumption or of initial and boundary conditions. And we have a dual solving problem. So we have to solve not only finding the ODE, but also have to solve the ODE itself. So in this work, we define a general family of differential equations, which are our governing mechanisms, our generating governing mechanisms. And then with our mechanistic neural networks, we learn how to do these three things simultaneously. So learn it, generate new ODEs and solve them. And the forward pass, we can just use the normal ODE solver. In the backward pass, we propose a neural solver. I'm not going to go into details, but because we don't have time. But it really works. There is algorithms like SINDI. Do you know SINDI? Like symbolic regression for dynamical systems. If you haven't heard of it, it's very interesting. It's a seminal paper from I think 16 from Steve Brunton. And it's like the go-to approach when you want to basically do regression to find coefficients of equations in your data. But this still has problems because it's not neural network based. It doesn't really leverage any neural networks. It's simply lasso regression, not linear regression, but like almost. So you can think of it as a single layer neural network, not even. Whereas here we basically bring the power of neural networks into representation learning. And this is a pity here because that was also a nice video where basically in the right-hand side of the slide, you would see how the model learns to actually generate the ODE, as well as over time the type of ODE, like the actual equation, but it learns to improve over time that describes the data. And you can use this for all sorts of things, like for linear discovery, non-linear discovery of physics, physical parameters, forecasting, interpretability. We also used it for instance, to compute the orbital forces of finite trajectories in a two-body problem. Again, here a problem was that in the absence of external information, constants create a problem. You don't know, for instance, anyways, too complicated. I think I'm running out of time. Happy to discuss after. And for me, what's an interesting question here is, I find this in a way very interesting for me, obviously, but in a way also I wouldn't say trivial, but okay, so what? Who cares? Because you're discovering an equation of something you already know. The very interesting thing is, can you actually discover an equation of something you don't know, from unknown data? Of course, there you've got the problem that, you have no ground truth in principle, so you have no way of knowing whether the equation is good enough or not. I think that's actually a very interesting direction for interdisciplinary research with physicists and maybe social scientists. You can really take it case by case. And last, very quickly, a couple of minutes. Assuming we've got the mechanistic, if we have mechanistic representations, we sort of assume these perfect state variables. In a way, until now we thought okay, segment anything will give it to us, and and this and that, which is again an assumption. It's a strong assumption. How would we know? How can our robot really? Can the robot just rely on sum forever and that's it? Ideally, we would like to have an autonomous way of learning. Like symbols, basically. And in this line of work from UII, Clear and ACML for the past 3-4 years, we investigated how we can do spatiotemporal causal representation learning in a very theoretical setting, actually. So the applications here are more mundane in that sense, but there's also exciting. What do I mean here is, temporal causal representation learning is the setting where you assume you've got, let's say, some sort of video, and in the case when I say the application is a bit more mundane, is the video is just simulation, no real video for the moment. And then you've got a robot, like a robot agent here, that performs an action, and based on this action, it can, something happens in the world, in the environment, something changes. And then the neural network that basically represents the world model gives feedback via representation back to the agent, so the agent can observe what happened in the world. And now the question is here, what kind of questions do we have from our representation, or what kind of expectations? Like, okay, ideally we would like to know, or to learn in our representations the causal variables of the environment. So basically, causal variable here is like variables that have a clear causal influence on what happens in the world. For instance, if I press the stops button, like fire will pop. That has a very direct causal influence, because when I perform an action, something very explicitly happens. Or the frying pan, it's another causal variable, because if you put an egg, it will fry. Generally, you can think of causal variables as from an inverse rendering perspective. If you were to recreate the world around and to reconstruct its graphics, let's say with Adobe or whatever, you would like to have these variables to control the lighting, like the various objects, what they mean and so forth, and all these are causal variables. Now, we also want to have how do they interact, these causal variables, with each other. Like when I push the starts button, something specific happens, like fire starts. That's a very specific relation that I want to learn as a robot, right? It's very important to know what happens when a specific button is pushed. As well as, I would like to have representations that can tell me how now my robot can interact with these causal variables in a controllable and meaningful way. In this model we have, as our causal model, it's a temporal directed acyclic graph. Our observations, our observed variables are images, and we've got also regime or robot variables, which is basically the coordinates of the robot arm. And these are also observed because the robot knows where its arm is, or it should know. And then the latent, so the things that we want to to learn in the process, are basically these causal variables and the interaction, so how we interact with these causal variables. And yeah, without going into details, the causal variables are connected through time, through the regime variables. So basically my robot arm, which are the coordinates, basically have particular influences, particular interactions. So you can think of it like the robot arm, when it goes to push the button, until then the robot only knows the coordinates of its arm. It doesn't know the action push. It only knows what its arm does. So this interaction variables is exactly like this pushing, like how you translate 3D coordinates into some sort of semantic action. And yeah, this worked quite well. Yes, I'm done now. This worked quite well, and in fact we presented an extension now in iClear in May, where we combined them with large language models, and the large language models basically guide this exploration, this discovery of causal variables, because until now everything was completely trial and error. So a robot performs various actions sort of randomly and infers what are the causal variables and the possible interactions. Now, if we have a large language model, it can give us a good prior. Like for instance, well, there is a stove, likely there are buttons, try pushing these buttons. And we also combine this with a segment anything model to autonomously to have also a good prior on the type of objects that we observe in the world. Yeah, so in the interest of time, next is I would like to scale this with real robots beyond simulation, and basically do this all simultaneously in the end. I don't know. Let's see. So as a let's say summary or conclusion, I think personally, physically grounded models are necessary for trustworthy autonomy. I think for me that's the thing missing right now from robots. I'm not a roboticist, but maybe from a bit outside, I find it hard to believe that robots will be trusted in open space otherwise. It's not a luxury, it's a minimum requirement for systems that operate in the physical world. As a next milestone, I think it's very important to understand what physical abstractions matter at which scales. We cannot have likely a model that works for everything. And statistical agreements, the usual benchmarking we have with computer vision, with human annotated truths, I think is not enough anymore. You've got a huge gap for unsafe behaviors to slip through the cracks. Yeah, and this is it. Thank you very much.
We have time for one question. Okay, please.
Thank you for the very interesting talk. I would like to ask regarding... Hello, okay. I'd like to ask you regarding the safety, because you mentioned it. Consider a vehicle that drives on its own and uses the physics-informed neural network. Do you believe that this optimization method of a neural network suffices to employ such a system on the real world, or because even if we achieve some minimality or maximality or whatever using these methods, still if we have like a 0.1% mistake, it would be fatal in such application. So,
Right. First of all, I have to clarify, physics from neural networks are not normally used for perception data. So in a way, we were one of the first proposed doing that. That I know of. Maybe there are more, but now, yeah, very interesting question. That goes a bit broader and depends on the application for self-driving. Like if we were to discuss self-driving in specific, I think there are legal barriers that are perhaps even more, let's say, like relevant. I think like self-driving is probably, I wouldn't say solved, but works quite well for 99% of the cases, let's say. But if you scale this up to 6 billion people, this 1% is like a few dozen million, right? And that's not good PR for anyone, or you also don't know who to blame in that case. So I think like there are many, many more problems. Now, perhaps more to the essence of your question, I think like a physics-informed network can basically inform you about how well the model understands the physics, and now whether these physics are correct or not depends on how good your assumptions are in the first place, how good your like detections are, how good like your segmentations are, because the physics are more or less correct. Well, that's not entirely accurate, but okay. So like to the extent that you can like marginalize out these errors yeah, I think it's like for this type of problems related to physical understanding, I think that would be good enough, yes. But I think like we're far cry away from anything like that. I don't think physics-informed models are ready for any such deployment any moment soon because they have not been proposed in the first place for this kind of thing. So we have to like improve them in that sense for this direction to like work.
thank you very much.
Cheers.
So we're going to have the lunch break now. We're going to resume the lectures at 2:30, all right?